to his name, Dr. Rimal Isaac. He is currently Assistant Professor in Nanotechnology at Nurul Islam Center for Higher Education, Tamil Nadu. He did his MTech in Industrial Biotechnology, Annamalai University, and PhD in Nanotechnology from Nurul Islam Center for Higher Education, Tamil Nadu. His area of interest and expertise is in nanomaterials, sensors, and green nanotechnology. He has teaching experience for 16 years and research experience for 15 years. He has published one book titled Nano the Science and Technology of the Small in the year 2023, received one patent for an invention titled Biosynthesized Gold Nano Formulation in December 2019. He has credit of having published 56 papers, 2 book chapters, and 10 conference publications, and has an H index of 12. He has been recognized for his contributions to the field of chemical engineering with numerous awards and honors, including the Outstanding Young Chemical Engineer 2007 award presented by the Indian Institute of Chemical Engineering. On behalf of the entire participants and faculties of MBCET, I take this opportunity to welcome Dr. Vimal Isaac to take over today's session. Over to you, sir.
So, good morning everyone. Hope I am audible.
Yes, sir. Audible, sir. Good morning,
Okay.
sir.
Good morning. So, thanks for the confirmation. So, first of all, I would like to thank Dr. Archana P. Das, head of the department, and the.
Sir, excuse me, sir.
Yes, madam. Yes, madam. Can you repeat? Can I continue?
Yes, sir, we can.
Okay. Thank you. So, first of all, I would like to thank the head of the department, that is Science and Humanist, Dr. Archana P. Das, then the coordinators, Ranjini M. Nair and Dr. Preeti PC for organizing such a program and inviting me one of the speakers. So, I will be sharing the presentation now. Hope the presentation is visible to everyone.
Yes, sir, it's visible.
Okay, thank you. So, today I will be speaking about the application of nanotechnology in the field of sensors. So, how I will go through the session is like, first we will see about the nanomaterials, how they are formed, how they can be synthesized, what are the properties. Then we will see about the various classification of sensors. Then we will see how nanomaterials can be applied in the field of sensors. So, this is the way the presentation has been split up. So, to continue with, we will start with nanomaterials. So, I hope everyone would have heard about the topic nanomaterials. So, what is nanomaterials means nothing. Any bulk material, when their size is reduced in the range of 1 nanometers, that is 10 nanometers or 1 nanometer to 100 nanometer, these materials are known as nanomaterials. So, any theoretically speaking, any material can be converted to this size by appropriate techniques. There are two types of techniques are there. One is top down and the other one is bottom up approach. We can use any of the two methods to convert any bulk material, let it be any hard material or soft material or polymer or metals, whatever material it may be, all the materials can be converted into this small size. But what happens when we convert the materials to the smaller size is very, very important. So, when you look into this nanotechnology, it is a multidisciplinary field, because most of the concepts what we are adopting in the nanotechnology comes from the basic of chemistry, physics and biology. As well as this nanomaterials is applied to all the fields, irrespective of all those, let it be civil engineering, let it be mechanical engineering, let it be automobile, fire technology, aerospace, aeronautical, whatever the field you take, even computer science, chip designing, all the fields this nanomaterials or nanotechnology is being applied because of the enhanced properties of the materials. So, this is the reason why, because everyone is telling nanomaterials or this nanotechnology is highly multidisciplinary. Anyone can come to this field or utilize the nanomaterials in their field for research and other purposes. So, we will have a doubt, because only in the recent 10 years or 20 years, we are speaking about this nanomaterials in a vast platforms. But when you look into the nature, these nanomaterials are being present in the nature. So, in the figure you can see this lotus leaf. When we are looking into the lotus leaf, we know this lotus leaf have an incredible property of non-stickiness, that when water comes into contact with this lotus leaf, the water will not stick to the leaf, it will run off because of the high hydrophobic nature of the leaf. So, when we look into the nano sized image of this lotus leaf, when you look into the nanometer size of this lotus leaf, what happens is there are some structures are there, regular structures are present in the lotus leaf. These structures are nothing but wax crystals, which is being present naturally in the lotus leaf. Because of the presence of these structures, what happens is like when water comes into contact with the lotus leaf, it gets flown away or it does not stick to the water leaf. So, this is because why the lotus leaf is having this water repellent properties. So, next when we look this abalone shell. So, these shells have hard structures. These hard structures are because of the presence of proteins which are in the nano scale present in these shells. This is the reason why these shells are having high strength. Although these shells are made up of calcium carbonate material, which is the less strength material, but because of the presence of these protein like structures which is arranged in a regular fashion, this shell is having the huge strength. So, next property is like butterfly wings. We all know this butterfly, they are highly colorful in nature, they are very beautiful, but when you look under a microscope, these butterfly wings do not have pigments. So, we know clothes we give color with the help of pigments. Because of the pigments present, the clothes are having color. But when we look into the wings of this butterfly, what is present is they have these special structures present in the wings. This is an SEM image. Because of the presence of these special structures, light falls on the wings and during reflection we can see these beautiful colors. So, these are some of the nanostructures which is already present in the nature, which gives special properties to living beings as well as non-living structures. So, next when we see why nanomaterial. So, here is the image of gold. Gold we all know it is yellow in color, it is a precious metal, it is an costliest one, everyone invest in gold. But when you convert this gold into nano form, so that is I told initially, any material can be converted into nano form provided the size of the individual particles is around 1 to 100 nanometers. So, for example, when we consider this gold is converted to a nano scale in the size of around 5 nanometers, it will have a color of red. So, this is one of the remarkable property happens when any material is converted into nanoscale. So, what happens is like the entire physical, chemical, mechanical, electrical, all the properties of the material changes when the material is converted to a nanoscale. So, that is why we are studying more about this nanomaterials. Even we know a lot about the bulk material, but when the size of the material is getting reduced, all these properties gets highly changed. So, when the property changes, we need to study again about the material. The property also depends on the size of the materials. So, what happens means a gold which is having a size in the range of 5 nanometers will have a color of red color. For example, we consider if the size is around 50 nanometers, it will have a violet color. So, this way the size will have a huge effect on the optical property of the gold nanoparticles. So, when we take for example, if you take diamond is a bad conductor of electricity. Bulk diamond if you take, it will not conduct electricity. But when the diamond is converted to nanoscale, what happens is the same diamond which is a bad conductor, it becomes a very, very good conductor of electricity in the nanoscale. So, this way any material if you take, the material's properties changes very much when the size of the material is converted to a nanoscale. So, this is the reason why even now when we make a new material in the nanoscale, we are forced to study all the physical, chemical, electrical, mechanical, all the properties of those materials. So, these properties of the bulk material cannot as such be applied to the properties of the nano materials. So, as I told, when you look here, so the size I told, the property depends on the size of the materials. The bottom left you can see the chart. Here what shows is there are different shapes are there. We have circle, we have triangle, we have rod shapes, we have cube shaped. So, all these are gold nanoparticles, but the size of the individual particles are different. So, not only the size of the particles, the shape of the particles also determines the properties of the materials. So, what are the properties changes is mainly the optical properties which defines the color, then band gap that defines the conductivity, then thermal properties, catalytic property, all these properties changes with respect to this nanomaterials. One of the remarkable properties of the nanomaterials is the catalytic property. What happens is when a material is being converted to a nanoscale, new surfaces are shown outside. So, nano means nothing, bulk material you are breaking down into smaller pieces. So, what happens when you break the materials to small pieces, new surfaces will get exposed. So, as new surfaces are getting exposed, what happens when you are using this material as a catalyst, more reactants can come and sit into the surfaces and the reaction will be very fast. So, this is one of the reason nano platinum is being used as a catalyst in the hydrogen production. So, the usage of nano platinum enhances the hydrogen production in water splitting reaction. So, when you look into the melting point, you can see the bulk material, or if the particle radius is around 10 nanometers, for gold the melting point is around 1000 degrees Celsius. But if the size is reduced to around 2 nanometers, what happens is the melting point also reduces drastically to around 500 degrees Celsius. The material is the same, it is gold, but what happens here is the reduction in the size happens, that is we are reducing the size from 10 nanometers to 2 nanometers, but the melting point of the material reduces by half. So, theoretically what we study is the material, whatever the material it may be, the melting point is same, it never changes, but when the material we convert it into a nanoscale, what happens is the melting point depends on the size of the particles. So, this chart what we can see here is different colored solutions are there. As I said, for gold, if you have a 5 nanometer solution, particle size solution, the solution will be red in color. As the size keeps on increasing, the color of the solution also changes, that is the optical property of the material changes and the color becomes violet in color. So, all these materials can be prepared with proper control of the reaction. If you have a proper control over the reaction mechanism or the reaction steps, you can prepare particles with different shapes, different sizes and different properties. That is, you can tune the properties of this nanomaterials for a particular application. So, that is the advantage of using nanomaterials in various fields. So, next when we are seeing classification of this nanomaterials. So, when you are looking into the nanomaterials, it can be classified into 0 dimension, 1 dimensional, 2 dimensional and 3 dimensional structures. 0 dimension means they will have few atoms. So, when you take the nanoparticles, I told the size may be around 1 nanometer to 100 nanometer sizes. So, if you take the 0 dimensional materials, their sizes will be less than 5 nanometers and they will have fewer atoms. And what happens is these atoms will be clumped together so that they cannot move in any directions. So, in all the directions they are confined very much, and what materials comes under the 0 dimensional is mainly the quantum dots comes under the zero dimensional material. They have remarkable properties. So they have remarkable optical properties when you are looking into this quantum dots, and they are very much used in this sensors applications. So next comes is nanotubes and nanofibers. Most of us would have heard about this carbon nanotubes. So all those carbon nanotubes comes under this one dimensional structures. So they are kind of rod like structures. So their thickness will be around 1 nanometer or something, but the length will be very huge, like 10 nanometers, 100 nanometers, or even 1000 nanometers length structures are there. So 2D are kind of, if you are able to make a nano material in the form of a film, then it is a 2-dimensional structure. 3-dimensional are polycrystals or bulk materials. So this is the classification we will see in terms of the size of the materials of nanomaterials. So next what we will see is synthesis of nanoparticles. So initially when I told there are two methods, or the synthesis methods are it is very widely classified into two types, that is top down synthesis as well as bottom up synthesis. So when you look into this top down synthesis what we take is, any material we take, we will break the material into small particles. Like we know this crushers are there. So they take big rocks and they break down into small sand like structures or coarse particles. So here also we are doing the same thing. We take the bulk material, we convert them into powder, still again we powder, we will get this nanoparticles. One equipment what they are using is ball mill. So what they do is, they will take the material, they will mix the material with strong balls, and they will put in a jar and they will rotate it. So what happens is, the balls will impinge on the materials and they will crush them, and the material will be converted into nanoscale. So this is the top down synthesis, that is from top or the big structures we are bringing down into the small structures. So next we have is the bottom up synthesis. Bottom up synthesis mainly are chemical synthesis methods. So here what we do is, we do chemical reactions or wet lab synthesis methods. We will take the atoms, we will build them into clusters, and then we will convert it into nanoparticles. Like we know salt, we have salt water. What we do is, we will put the salt water under the sun. So what happens, the concentration will increase and nucleation happens, and this nucleus will grow into big structures. So here also same thing, the atoms are present in the solution, they will form small crystal structures, they will grow and they will form these nanoparticles. Sometimes what happens, these nanoparticles can grow and become these bulk particles. If you have full control over the reaction, what you can do is, you can stop the process when nanoparticles are formed. So this way what you can make is, different shapes of nanomaterials you can make. You can make zero dimensional, you can make tubes, you can make rods, you can make sheets, you can make bulk nanomaterials also. But cost effectiveness, when you see of these two methods, the top down synthesis method is very, very cost effective. Why cost effective means, you can make nanoparticles in bulk quantities in the top down synthesis. When you are looking this bottom up synthesis, it is not that cost effective, because every synthesis methods you will get only small quantities of the material. But what's the advantage between the two methods is, bottom up synthesis method is highly advantageous. Why? Because you get uniform size particles. If you look into the top down synthesis, although it makes huge amount of nanoparticles, but each particles will be of different size and shape. You cannot get uniform sized particles in case of this top down synthesis. So this is the disadvantage and advantage of the processes. If you need bulk, and if you are not thinking about the size and shape of the particles, you can go about top down synthesis. If you want less amount and you need high size or controlled size and shape or uniform size and shape of the particles, you can think about this bottom up synthesis. So because of this small quantity that we will synthesize with a unique or same size or shape over the range of nanoparticles, the price of the nanoparticles are very high. So if you look into the price of carbon nanotubes, if you need to get a 98% pure carbon nanotubes of 1 gram in quantity, the price will come around 1000 to 1500 rupees. If you look gold nanoparticles, it will be in 10,000, 20,000. 1 gram gold nanoparticles, if you need, it will be more than 20, 25,000, because the gold salt what you are using for synthesis itself is come around that is 0.5 gram itself come around 7,000 to 8,000 rupees. So, although nanomaterials are costly, but when we look into the advantage of this nanomaterials, they overcome the price point. So, that is why everywhere we are using this nanomaterials. So, these are the things what we have seen. So, these nanomaterials can be used in all the places. So, it even though I told they are having difference in melting point when the size is being reduced, they are highly stable materials. Even in ambient conditions, these materials are highly stable, their properties will not change. At that small sizes also, their properties remain uniform, so that it is useful for all sort of applications. So, as I told, first we have seen about the nanomaterials, now we will see about the sensors. So, I hope everyone would have seen sensors, and we are using sensors every day in our life, right from our mobile phone have number of sensors. If you go to a shop, they have this gas sensors are there to detect the fire systems. So, when you are looking into the parts of the sensors will have a transducer. So, transducer what it does is it converts the energy from one form to another. But what is the difference between this sensors and the transducer is, sensor converts a physical parameter into an electrical output. So, we have a microphone. What this microphone does is, it captures the sound, it will convert it into a electrical signal, so that it can be measured or it can be transmitted over a distance. Here also what we do is, in all the sensors what we are using, some quantity we will be measuring. The quantities can be either resistance, it can be capacitance, it can be current, it can be voltage. So, these are the parameters what we will be measuring using a sensor, that is all the sensor parameters, let it be pressure, let it be temperature, let it be humidity, let it be gas, whatever the parameters it may be, all these parameters will be converted into an electrical signal by using this sensor, so that it can be measured using a circuit and it can be quantified. So, this is what happens in a sensor. Then one more thing is there, actuator is there. What it does is, it converts the electrical signal into an physical output. So, this is example is speaker. So, what it does is, when a microphone is connected to an speaker, what happens? This microphone will convert the sound to an electrical output. This electrical output, when we give input to an speaker, it will convert the electrical output into an same audio, it will be converted. So, this is what happens into an actuator. So, today we will be seeing about this sensors. So, when you look into the sensors, there are two types of sensors are there. One is an active sensor and other one is a passive sensor. So, if you look into the active sensor, what happens is, a sensor which produces an electrical output to an physical stimuli, it is known as this active sensors. Here example what it is given is an solar cell is given. Solar cell, what happens is, like when light falls on the solar cell, it converts the light energy into an electrical energy. In turn, it produces electrical energy. So, another example for this thermocouple, which is used for the measurement of temperature. So, when we introduce a thermocouple into a increased temperature or at a high temperature, what happens is, this thermocouple, because of the increase in temperature, it starts to produce some potential difference. So, this potential difference is proportional to the amount of or the intensity of the temperature present in that area. The same way, the solar panels are also, we know, the solar panels also produce the electrical output in response to the amount of the light it receives. If the intensity of the light is high, the more amount of current will be produced. The intensity is less, means less amount of current will be produced. So, this is the property what we are using in sensors to quantify the signal. So, then we have is the physical sensors, or the passive sensors. So, here what happens is, in passive sensors, we need to apply some potential to the circuit or the element or the sensing element, we need to apply the potential. So, because of this potential will be flowing through the circuit. For example, you have this thermistor. So, in case of this thermistor, what happens is, we will be measuring the temperature. current will be flowing through the thermistor. So, this thermistor will have a resistive material. So, the property of the resistive material is like when there is an increase in temperature, the resistance of the material will increase. When there is a decrease in the temperature, the resistance will decrease. So, what happens is when the resistance increases, the flow of current will decrease, and when the resistance decreases, the flow of current will be increasing. So, here also we are measuring the potential that flows through the, or the electricity that flows through the circuit. The flow of the electricity depends on the resistance of the material. In turn, the resistance of the material depends on the atmospheric temperature. So, in the previous case, active sensors, we will be applying the potential. In case of in the case of the active sensors, the sensor will produce the potential. In case of this passive sensors, we will be applying the potential. Because of the change in the property of the material, we will be measuring the sensing signal. So, there are also different types of this passive sensors. We have this photodiodes, we have this thermistors, we have this strain gauges, etc. So, this is how the sensors are classified. So, we will see individual type of sensors. First one is we will see about this resistance sensors and measurement. So, here one example is the strain gauge. The strain gauge is used for measuring the force, or any flexible areas we can use this to measure the force. So, what happens is this is an sensing material that is coated over, or it is created in a pattern over a flexible film. This film can be a PVC film. Most of the cases what they do is they will use the screen printing. So, screen printing we all know it is mainly used to create design in clothes. It is also used in electronic field to transfer patterns on a circuit. So, we know this carbon, we have carbon paste is there, carbon mixed with polymers with some solvents. So, this carbon paste, what we can do is we can mix with some sensing elements, we can use it as an ink and screen print over a circuit. We can screen print over a circuit. So, the solvent will get evaporate and the circuit will stay on the film. Not only carbon paste is available, silver paste is there, gold paste is there. So, all this they will tell it as an carbon ink or gold ink or silver ink. So, all these pastes are normally available. You can buy that, you can prepare a sensing material, add to that ink, use screen printing, coat over a substrate that can be a PVC film, polyvinyl chloride film, it can be a silica substrate, any substrate you can use, coat it over, you can connect to a external circuit, you can do the experiment. That is a simple one. Here also they have done the same thing, transferred the patterns over an PVC film. What happens when their PVC film flex, it changes the resistance of the material. So, based on the resistance, if more flexibility you are applying to the film means more resistance will be produced and the amount of current flowing through the circuit will be minimal, and with the less flexibility means what happens, the amount of current flowing through the circuit will be very high. So, this is an directly proportional, and you can use some, the signal will be analog, you can use some analog to digital converters like Arduino or ESP8266, some external circuit you can use. Those circuits are very friendly circuits, they cost also very less than 1000 they cost. You can buy them, integrate these sensors along with that circuits, they will convert this analog signal into digital circuit, and you can create the relation between at how much force you applied and how much is the resistance produced or how much is the current flowing through the circuit. You can create a relation, you can have a calibration graph, from that you can find out how much is the force applied to the circuit. So, this circuit works on the principle of resistance measurement. So, another one kind of resistance circuit is like piezo-resistive sensors. Piezo-resistance means what happens, there are certain crystals are present, quartz is also a piezo-resistive material, polymers are also there, some are the polymers are piezo-resistive polymers are there. What happens when you apply some force to these crystals, what happens, they will produce some electricity. It can be reverse also, when you apply some electricity to this material, they will start to vibrate, crystal vibrations will happen. So both the cases you can take. So either you apply a force to the material to produce electricity, or you apply some electricity to the material to apply some force. So these kind of piezoresistive materials are used in atomic force microscope. So atomic microscope is a kind of measurement device like scanning electron microscope. So this microscope, what it does is you will have a 3D mapping of the materials. So we all know we took photographs of some image. So if you want to look into the size and shape of the nanomaterials, normally what we do is we will use transmission electron microscope or scanning electron microscope. So what they do is they will give only 2-dimensional image. So if you want to have a 3-dimensional image, you can go for atomic force microscope. So what they does is it will measure the 3D mapping of a sample. You will get the shape of the samples also. So there what happens is the stage will be there in the bottom part. The stage has to be moved in nanometer level. So there what they do is they will use this piezoelectric crystal. So what they does is if you provide less amount of electricity, the crystal will move certain distance. So that way they will control the piezoelectric crystal by applying this current to move the stage in a high precision level in the range of nanometers. So this is one very industrial application of this piezoresistive materials. So where we are using this piezoresistive materials is it is used as a pressure sensor. So where they are using is they are using it as an ear to make the ear damaged people hear. What happens is this is an implant. So this is an MEMS based implant which is having these piezoresistive sensors which will be placed inside the ear. So the circuit will be connected to the patient to the cochlea. So what happens is when sound falls on this piezoresistive sensors, it produces some current. So the intensity of the current depends on the sound. So we all know most of the signals in the human body is also transmitted by electrical signals internally. That is the flow or movement of electrons happens. So here what they do is they use MEMS sensors. So it responds to the sound. The sound will be converted into an electricity. They have been using this circuit to properly convert the sound to an electrical signal, and it will be transmitted to the patient so that they will have their hearing capability. So this is one of the widely used medical application of this piezoresistive sensors. So then we have this capacitance sensors. We all know capacitance, that is the charge that we measure between two plates. The charge depends on the distance of separation between the two plates and the permeability or what material is present between these two plates. So this is used in measuring pressure or the blood pressure measurement it is being used. So what happens is there are two plates are there. In between the two plates one mercury drop is present. So this mercury drop has a property that it will not flow, it will not form a thin film, it will stay as a drop if it is placed in a very small quantity. Same way this mercury drop is placed in between these two layers. So what happens is we have the first layer, then we have this ceramic dielectric layer, then we have the third layer, that is the connections are made using aluminum, then the terminals are connected. In between these two aluminum layer we have this ceramic dielectric layer as well as the mercury. Above the mercury one diaphragm is there, a thin film is there. So what happens when a pressure is being applied from the top, this will exert some force on the mercury and the shape of the mercury will change. So what happens, it will flow in between the two plates. So the distance of separation decreases, there is an increase in the dielectric material inside. So when the pressure is being applied, the change in the capacitance happens because of the change in the area between the two plates and the material shape between these two plates. So this is directly proportional to the amount of force or the pressure applied. So this can be correlated to the patient's blood pressure. So this technology is used for measuring this non-invasive blood pressure measurement. So the next we have is the photoelectric sensors. So these sensors are mainly used to measure the distance or objects or presence or absence of an object. So here what happens is, there are certain material, we have seen this solar cell, what happens when light falls on these materials, they will produce this electricity. So here also the same thing happens, they convert the light signals into electrical signals. So where it is being used is, it is mainly used in this pulse oximeter. So what happens in pulse oximeter is like, in the pulse oximeter, light will flow through our fingers. So in the bloodstream there will have oxygenated blood as well as deoxygenated blood. So these blood having different amount of absorbance to the light. So here what we are using is, we are using two light waves of two different wavelengths, one is 660 nanometer and the 905 nanometers. These two light waves are having different absorbance maximum. So this difference will be calculated, and from that we will be able to calculate how much amount of the blood is oxygenated, and from that only we will be able to measure the P-O2 of the blood. So this pulse oximeter utilizes the principle of photoelectric effect. Next one is the ion sensors. So these sensors are very widely used. One of the widely used sensors next to this gas sensors is the ion sensors, because ion sensors can be employed to measure all sorts of ions. So ions means any material can be converted. Ion means we can convert into ionic form, Fe2 plus or Fe3 plus we can convert. Such way any material can be converted to ion when it presents in solution. So we have sodium chloride. When we put sodium chloride in water, what happens is it converts into Na plus and Cl minus. So these ions can be detected using this ion selective electrodes. So when you are looking to the construction of this ion selective electrode, what happens is like, though these ion selective electrodes have a reference electrode and the sensing electrode. So in the sensing electrode, at the bottom part it will have a membrane. So this membrane is known as the ion selective membrane. So this membrane is highly responsible for the selectivity of the ions. We have this pH electrode. So every lab, chemistry lab or civil labs will have this pH electrode. So in the pH electrode, what it has is this membrane is selective to H plus ions. So we all know that pH is the measure of this hydrogen ions. So here also the same thing happens. So this membrane is highly selective to H plus ions. So if you are going to detect sodium ions, means the membrane will have high selectivity towards Na plus. Because of this selectivity, what happens is the ions present in the solution will come and bind to this surface. When ions bind to the surface, what happens is there is a localized potential difference will happens, and this potential difference will be measured through the circuit. So this circuit is an high impedance circuit. The impedance will be in the range of 1000 mega ohms or something. It is a very high impedance circuit. So need to create an external circuit which can be used to isolate the potential from this high impedance circuit. So this is what happens in case of an ion selective electrode. So this is a typical calibration graph. So calibration graph is nothing. What happens is you will test the equipment or the electrode at different pH ranges. So we all know that if you take any sensors, the sensor cannot be used for a wide range. For example, if you take a thermometer, we will be using thermometer for measuring the fever. So it will work maybe from 20 degrees Celsius to maybe 35 or 40 degrees Celsius. You cannot use it to measure 50 or 60 degrees Celsius. So if you have a lab scale thermometer, means it may go from 10 degrees to 100 degrees or minus 20 degrees to 300 degrees. You cannot use beyond that. So all the sensors is having a working range or a detectable range, that you need to know before you are going to apply for a particular application. So initially we saw this thermistors, that small black color thing. So that thermistors you cannot use beyond 150 degrees Celsius. Thermocouple I have told, these thermocouples you can use it even above 1200 up to 1500 degrees Celsius temperature measurements you can use. So that is a working range. So here also the same thing, we will be using this calibrate these kind of graphs to detect the range in which you can use the equipment. So before using any sensors, you need to look into the data sheet of the sensors and find out what is the working range, what is the resolution, what is the minimum detectable limit, what are the interferences. So this is an ion selective electrode. I told this electrode will work more specifically towards H plus ions. Sometimes these electrodes may also have cross interference. It may also produce a signal when there is Na plus ions is present. For example, I am telling. So these interference also you need to know before using these sensors in any practical environment. So these are very, very important in selecting an electrode or an sensor for particular application. So this is an chart which shows the different ions, the different analyzers and the company which is manufacturing this ion selective electrodes. Not only this is just for an chart I am showing, there are many ion selective electrodes are there made by many companies. They are used in labs as well as very industries they are using. The widely used sensors are like this gas sensors. Gas sensors we all know it is being used everywhere. Even houses also nowadays using for fire extinguisher purposes, because when fire is there, this smoke will be generated. This devices will sense the smoke, it will give the signal to the circuit and immediately water will be sprayed and the fire will be stopped. So here what happens is, in most of the gas sensors, it will have a sensing element. So what happens is, this gas sensors will have a sensing element. Above that some material will be deposited. Most of the cases metal oxides are used as the sensing element. So tungsten trioxide it may be, zinc oxide it may be, cadmium oxide. So these are some of the oxides. I told the properties of the material changes with size and shape. So particular materials they will coat above a substrate, and this material will sense the presence of a particular gas. Hybrid materials also there, metal oxides also there. So this will sense the gas. But one of the problem with these gas sensors is, you have the sensing material. When gas molecules comes and sits above this sensing element, sensor will work, it will give the signal. But what happens when an gas material comes and gas molecule adsorbed on the surface, it will not immediately get removed. So sensor should work in such a way, we have a thermometer. When we measure the temperature, it should show the actual temperature. When we remove the thermometer, it should come back to the original state. But in case of a mercury thermometer, what we do is, it will not come immediately to the original state. If you keep it for say like 2 hours, 3 hours, it will come to the original state. Otherwise what we will do, we will shake it off, so that the mercury will come to the bulb. So in gas sensors that will never happen. What happens is, when gas adsorbs on the surface, it will stay there and will get adsorbed. So in order to prevent that, what they do is, all the gas sensors works at a high temperature. I told about the substrate, right? Below the substrate there will be a heat plate will be there. So this heat plate will heat the sensing element, maybe like to 60 degrees or 70 degrees it will heat. So what happens, when the temperature increases, we all know molecular motions will be very high. So as the temperature gets increased, this gas molecules will come and sit above the surface of the sensor until immediately will get evolved. So the sensor senses comes back to its original state. So that is the reason, when you, if you have the chance of looking into any gas sensor or a gas sensors, when it is working, you touch that, it will be hot. This temperature is because the gas sensor is being heated purposely, so that to avoid the adsorption of gases above these materials. So this is the principle behind this gas sensors. This gas sensors we all know, for all the gases we have gas sensors. Let it be nitrous oxide, let it be carbon dioxide, let it be petrol, let it be diesel, let it be LPG. So any gases, methane, formaldehyde, any gases you take, there are gas sensors available in the market. So, this is an example of a breath analyzer which is used for detecting the any harmful gases are present in our breath or something. To detect that, they are using this breath analyzers. Nowadays, what they are using, research is also going on to identify cancer utilizing the gases coming from a patient's mouth or nose. So, these kind of research are also going. So, then we have this humidity sensors. Humidity sensors are used to measure the amount of moisture in the atmosphere. So, here also same thing as I told, initially kind of a flexible sensor. One substrate will be there. Above the substrate, the material will be coated. When the water molecule sits above this sensing element, the resistance of the material changes. The resistance depends on the amount of humidity present or the amount of moisture present. From that, we can measure the amount of humidity present. These humidity sensors are mainly used in humidifiers. So, when you look into the hospital, patients will be given oxygen to breathe. But if a patient is given for a very long time dry oxygen for breathing, what happens is he may have some tissue damage or he may go into some infections in his lungs. So, in order to prevent that, what we do is we will be use some humidifiers, mix some amount of moisture with the oxygen, then it will be given to the patient in order to prevent all these complication. So, in that case, you need to know how much amount of humidity to be applied. So, in that we will be using the humidifiers which are fitted with this humidity sensors, which will control the amount of humidity in the sample. So, so far we have seen the different type of first we have seen the different type of nanomaterial, their classification, then we have seen the different type of sensors. Now, we will see what nanoparticles we can use for these sensors. One of the widely used nanoparticles is gold nanoparticles. Why gold nanoparticles means? Gold nanoparticles are easily, it can be synthesized. It can be easily synthesized in any size, any shape what you require. Other materials, you need specialized equipments. If you take carbon nanotubes, you need specialized equipments to manufacture. Next thing is gold nanoparticles are not that toxic. You can synthesis in your lab itself. If you look into this cadmium oxide carbon dot nanoparticles, this cadmium is little bit toxic. During the synthesis, more fumes will come. That fumes are also toxic. So, you need some specialized kind of hoods to synthesize these nanoparticles. Gold nanoparticles, you know, there is no such toxicity involved in the synthesis of these nanoparticles. They are highly stable. They can be prepared in any size and shape. They are highly conducting. Only thing is cost. Cost will be very high. So, because of these properties, gold nanoparticles are used in all sensors. Not only in chemical sensors, physical sensors, biological sensors are also these gold nanoparticles are used. Why gold nanoparticles are used in biological sensors means this gold has the capacity to bind easily to the sulfate ions. So, most of the proteins if you take, they will have sulfate ions in their structure. So, these nanoparticles can be easily bond to the gold, bond to these proteins which have this SH bonds. This is one of the reason because gold nanoparticles are widely used in biosensors. So, if you look into most of the biosensors, one or the other way gold will be used. So, the presence of this gold, what happens? It enhances the signal. So, even a small amount of sample is present also, when you have this gold nanoparticles, the signal will be amplified when you measure using some optical methods. So, here are you can see some different gold nanoparticles used. We have this nanorods, nanoparticles are there, dots are there like quantum dots, composites are there. Composites means not only gold, gold is mixed with some other materials. We have nanopores, wires, pillars. So, here for what they are using is these nanorods are used for detecting this hepatitis B virus. So, it is used for detecting this fetoprotein, then it is used for detecting streptomycin. Even gold dots are also used for measuring this HIV virus. Then it is also used for gene sequencing. Here you can see these materials are used for gene sequencing. It is also used for detecting pesticides, not only for biological purposes in the detection of some diseases or disease causing agents. it is also used for detecting pesticides, which is helpful for environmental purposes. So here you can see the same thing given as a image, dots, nanowires, rods, particles. It is used for gene sequencing, streptomycin, that is a protein, virus detection, also for HIV virus. Next we have this carbon nanostructures. Why I am showing this carbon nanostructures and gold means gold I have shown the advantages. Carbon nanostructures, carbon exists in different forms. Even if you look into the carbon nanotubes, a single carbon nanotube, there are also multiple wall and single wall carbon nanotube, one such classification. If you look into the single wall carbon nanotube, both ends closed nanotubes are there, one end closed nanotubes are there. Multi walls are also same thing, one end closed, both end closed are also there. This carbon nanostructures can also form fullerenes, buckyballs, these kind of structures. There are also different classification of C60 is there, C80 is there, that is the number of carbon atoms, C180 is there, different type of structures are there. The backbone is carbon, but it can form different structures. We are also know bulk carbon based structures. If you look, we have this diamond, that is also carbon. We have this graphite, which is also carbon. The same kind of structures in the nanoscale, they form various structures like carbon nanotubes are there, buckyballs are there, fullerenes are there. Those things we give it as a common name as carbon allotropes, we will tell. So because of the different forms carbon can form, it is used in various applications. Carbon also same thing like gold, it is also a very good conductor of electricity. Carbon itself is a conductor, but when it is converted into a nanoscale, it becomes a much better conductor of electricity. As I told initially, we know diamond is a bad conductor, but when the same diamond is converted into an nanomaterial, it is a very good conductor of electricity. The structure seems the same, that is the atomic arrangement it stays the same, but the color changes. Diamond, if you look, the color of diamond is white or transparent, but when you look into the nano diamond, it is black in color. So because of the various materials or the various structures present of this carbon, I am giving carbon as one of the example. So here you can see carbon nanotubes, it is mixed with polymer composite, which is used as a protein sensor, which is used in ELISA. ELISA is nothing but enzyme linked immunosorbent assay, which is used mainly for detection of proteins. Some viral proteins, if it is present, you can use this method to detect. Then we have this carbon or Teflon composite, so it is used as a glucose sensor. Then we have this multi-wall carbon nanotubes, which is used in the detection of DNA fragments. Graphene sheets are there, which is used for various detectors like glucose, DNA, gases, heavy metals, ions. Then DNA wrapped in multi-wall carbon nanotubes. It is also used for the synthesis of glucose, peroxidase, pesticides, proteins and ions. So this carbon cost is less. I told if you take gold, the cost is very high. 1 gram of nano gold, if you want to buy, it will go above 15,000 to 20,000. But if you take carbon nanotubes, more than 98% purity, 1 gram if you want to buy, with 1,500 rupees you can buy. So that's one of the reason carbon is also being used in most of the applications because of this low cost. So these are the two main materials which is used widely in sensors. Then we have this metal oxides. This is another class of material which is mainly and widely used in gas sensors. So we have different materials like titanium dioxide is there, zinc oxide is there, indium trioxide is there, copper oxide is there, tungsten trioxide is there, any iron oxide is there. So what happens is these materials will stay as the sensing elements. So when gas comes on, sits on this material, what happens? As I said, the resistivity changes. Immediately the amount of current flow will decrease. The resistivity depends on the number of molecules sitting above the sensing element. So by this way you can sense a gas. So here I have given pure metal oxides, but nowadays they are using hybrid metal oxides, doped metal oxides, metal oxides along with polymers, metal oxide along with metals, metal oxides along with carbon materials also, like hybrid materials nowadays they are using, because most of the study with pure materials has been outdated. So now what happens, they are using hybrid materials which is having more sensitivity than pure materials. That is one of the reason, because they are moving towards this hybrid materials. So these materials can be made easily in a chemical lab. So what are the chemicals you need is, you need some nitrate salt. I am telling about simple method. You need nitrate salt. If you want to make this zinc oxide means you need zinc nitrate. So what you can do is, you can take zinc nitrate, mix zinc nitrate with some fuel. Fuel, what you can do is, you can take urea. Urea is a very good fuel. Why urea becomes fuel means, any material which contains high amount of nitrogen, this urea contains nitrogen. That's why we are using urea as a fertilizer. Any material which contains high amount of nitrogen, that contains as a fuel, that will burn easily. Nitrogen will help in burning. So mixing zinc nitrate, it also contains nitrogen. Urea, this also contains nitrogen. Mix these two things in water, heat it around 150 degrees Celsius. That is enough. 150 degrees Celsius, if you heat, what happens? Initially water molecules will burn off. Then this material will become hot and it will burn off. All the nitrate carbon materials will move away. Finally you will get zinc oxide nanoparticles. This method name is combustion method. This is a top down method. This is one of the simplest method by which, in a simple lab, you need a stirrer, you need a setup for heating. These two setups if you have, you can make any metal oxides in your lab. So we have seen the materials which can be applied in, which is applied in sensors, like we have seen metal oxides, metal as well as carbon based materials. So these are some of the examples given here. In case of this metal oxides, I told tungsten trioxide is being used. It is used as a nano wire. It is used for the synthesis, reduction of hydrogen, LPG, ammonia. Then silver vanadium trioxide nanowires are prepared. It is used for the reduction of hydrogen sulfide. Cadmium oxide, molybdenum trioxide is there, copper oxide is there. So you can see here, I told metal oxide loaded with metals also they are using. So here you can see copper oxide is loaded with gold, copper oxide loaded with platinum is there, vanadium trioxide loaded with silver is there. So loaded with polymers are also there. So this graph is the response graph. So what happens when they apply the gas, the signal, or here the resistance they are measuring, the resistance decreases. So that depends on the material. It can be positive or it can be negative. Some materials during the sensing the resistance will decrease. Some material, when the sensing happens, the resistance will increase. That depends on the type of the material. That is known as the positive response or the negative response. Here what happens, the resistance decreases. So when the gas is withdrawn, it has to come to its original stage. So that is why I told. So this won't happen easily in case of a gas sensor. That's why commercial sensors, what they do is, they will heat the substrate to a high temperature, so that sensing happens. Once the gas is, or the sensing material, sensing physical phenomenon is removed, the sensor comes to its original state. So this is about this metal oxide based gas sensors. This is one work we did in the year 2015. There is an old work. So here what we do is, we prepared an carbon paste electrode. I told we can easily prepare carbon paste. In order to prepare carbon paste, you need just two materials. One is the graphite powder, other one is the paraffin oil. So what you have to do is, you can take paraffin oil, mix it with graphite in proper ratio, put it in some holder, polish it, you have your electrode. For example, you need to incorporate copper oxide or zinc oxide or any material along with the electrode means, what you have to do is, while preparing itself, take graphite, take copper oxide, take paraffin oil, mix it, grind it properly, put it in a holder. Glass holders you can use or plastic holders you can use. Push it, another end you insert an copper or a silver wire for conductivity. use some good multimeters which can measure least amount of current or potential, like in the range of micro or nano amperes or nanovolt or microvolt. Use some good multimeters. If you have a setup for measuring current or potential of a sensor. So this way you can prepare electrodes. Preparation is very easy, not complicated. Graphite is available in all chemical stores. Paraffin oil is also available in all chemical stores. Metal oxide, I told you can prepare it very easily. So here what we have done is we use this for detecting zinc metal in solution, not in solid form, in solution. So this is one such work we have done and we have prepared. Currently I am working mainly on metal oxide based gas sensors. So next thing is gold. Also I have been speaking. Gold is also gold nanoparticles can be also prepared very easily. So we need the gold salt. It can be reduced to gold metal. So how it can be reduced is you can use trisodium citrate or sodium borohydrate. Only thing is you need to know the optimum amount of this trisodium citrate so that you get gold nanoparticles of a particular size. So if you add more amount of this trisodium citrate, what happens is, initially I have shown a graph. You have color rangings of gold from 5 nanometer, you have red color, 150 nanometer, you have violet in color. Immediately you will get a particles of huge size. So the reduction of gold is very fast. In 5 minutes it will not take. 2 to 3 minutes you will get to the gold nanoparticle solution. What you have to take is, you have to take chloroauric acid or hydrogen tetrachloroaurate, mix it with trisodium citrate. The quantity is very essential to make particular sized particles. What happens is, the color of this gold salt solution will be yellow. So when you add this trisodium citrate, what will happen? It will immediately change to some color, let it be red. So for example, we know the correct quantity and we added the correct quantity. We prepared a 5 nanometer sized solution. So this color will be red in color. This same chemical can be used for preparing copper nanoparticles, copper metal nanoparticles, silver metal nanoparticles, platinum metal nanoparticles, palladium metallic nanoparticles. Same procedure. You need to optimize. So here chloroauric acid you will be using. There you will be using silver nitrate, platinum chloride, palladium chloride. So these kind of salts you will be using. The reducing agent remains the same, trisodium citrate. What happens? This trisodium citrate will reduce the metal salt to metal atoms. So you can prepare gold or metal nanoparticles easily in your lab. So this is kind of a sensor. So here what happens is, we have this gold nanoparticles. So this can be easily tested in our lab for a sensor. What happens is, we have gold nanoparticles. When you add sodium chloride to this gold nanoparticles, what happens is, it will form a blue color solution. So what happens here is, as we know why blue color forms is because the particle size increases. Same thing happens when we add sodium chloride to the solution. This sodium chloride causes agglomeration of these nanoparticles. So as the particles join together, it will form blue in color. This can be used as a sensor for measuring sodium chloride in solution. You add some gold nanoparticles to a sodium chloride solution. Based on the color intensity, you can tell, need to have an UV visible spectrophotometer to measure the intensity of this color. You add certain amount of gold solution. From the color of the solution, you can tell how much amount of sodium chloride is present. So this is a simple lab experiment to demonstrate a chemical sensor for students. So that's all about the presentation. So I hope I have covered everything, right from type of nanomaterials, then type of sensors, and how nanoparticles are being used in these sensors. So I am from Nurul Islam Center for Higher Education. So I am working as assistant professor in Department of Nanotechnology. So this is some of the facilities what we have in our department. So we have this HRD, AFM, electrochemical oscillation, particle size, ultra pure water setup. We have UV visible spectrophotometer, surface area analyzer. So we do consultancy. So that is anybody can utilize our facility. They can come, they can do the analysis by paying the appropriate fees for the analysis. So this support we provide to industries, academicians, that means research scholars or faculty, students. So everyone we extend this support. So thank you for providing this opportunity. So if you have any questions, you can ask now. So this is my contact details. So if you have any doubts or if you need any support, you can contact me. So thank you. Madam?
Yes, sir.
Yeah. Any questions? If they have, they can ask now, madam.
Thank you, sir. The participants can now put forth their